Hi everyone, I'm Vikram Ramaswamy, and today I'd like to talk to you about fair attribute classification through latent space debiasing. This is joint work with Sunnie Kim and our advisor, Professor Olga Russakovsky. In current datasets, certain attributes like gender tend to be correlated with certain tasks, like cooking or coding. Let's say that we want to train a hat classifier, and wearing hats is correlated with a gender. Then, such a classifier might pick up on gender cues rather than hat cues. Or, similarly, suppose wearing hats is correlated with wearing glasses, as shown here. This classifier might only recognize hats in the presence of glasses. What we want, ideally, is a dataset wherein these two attributes are independent. However, it can be hard to collect huge amounts of data from the real world that is unbiased. One possible workaround is to use GANs to generate a synthetic dataset instead and augment our real images with these synthetic images. As a quick overview, here's how we can use GANs to augment our data. We can sample random vectors z in the latent space and use a generator to get an image for each latent vector. We can then hallucinate labels for the synthetic images using a model trained on just the real images, and then train an attribute classifier on both the real and the synthetic images. An interesting observation made by Denton et al. Was that the latent space of a GAN is quite structured, and in fact, most semantic attributes are approximately linearly separable in the latent space. This is our first idea. Using a linear SVM classifier, we can learn the hyperplane for glasses, as shown in the image. Now, given a latent vector z, we can compute a vector z prime that flips the glasses score. This allows us to compute pairs of images, one with glasses and one without. The issue with this, however, is that we have no control on whether or not an image generated from z prime has a hat. In fact, naively perturbing latent vectors in this way can maintain biases. For example, when adding glasses, we also add a hat. Since we want to control the hat attribute as well as the glasses attribute, we now compute hyperplanes for both glasses and hats. Given these hyperplanes, we can now compute a hat score and a glasses score for every latent vector z. We can then compute a corresponding z prime that has the negative of the glasses score but the same hat score. The intuition here is that both z and z prime are either wearing hats or not wearing hats, and one of them is wearing glasses while the other one is not. Computing our balanced synthetic dataset in this way has many advantages. The first one is that our method can use a single GAN to decorrelate multiple target protected attribute pairs, whereas previous works require one GAN per attribute pair. This method also preserves the intra-class variation of the attribute. Consider an attribute like smiling. This attribute ranges from not smiling to partially smiling to smiling. Since the z's are chosen at random, a similar distribution exists in the synthetic dataset. The final advantage is that the samples are generated to maintain an independence between the target and the protected attributes. We'd like to understand how well training with a balanced synthetic dataset can do. To do so, we use a CelebA dataset and train attribute classifiers for 26 different target attributes. Since we care about fair classification with respect to a protected attribute like gender expression, we measure the performance of our model using 4 different metrics. The first metric, average precision, is a threshold invariant accuracy metric. We also use 3 other fairness metrics: difference in equality of opportunity, bias amplification, and the KL divergence between score distributions. We find that training with a balanced dataset suffers a small loss in AP but performs better on all 3 fairness metrics. Our paper includes other results such as ablation studies of other perturbations, analysis of when our method performs well, and comparisons to prior work. To conclude, we find that our proposed method is effective in reducing bias in visual attribute classifiers. One current limitation is that this method just decorrelates 2 or maybe 3 attributes. It's possible that when doing this decorrelation, we are adding bias along yet another attribute. For future work, this is something we can try to measure and eliminate. If you're interested in this work, here are a few links to check out, including the code. Thank you.